So far, you guys have been doing great with transformations of absolute value functions. So now we want to talk about how these transformations relate to all different families of functions. So I want to alert you to what I feel you should be responsible for. You should be responsible for understanding and recognizing all linear functions. You should be responsible for recognizing and understanding all absolute value functions. Along with the absolute value now, you should be able to transform algebraically any given absolute value function. What we want to move on to now is some new stuff. So the new stuff will be the quadratic, the cubic, and the square root function. So let's just take a look at what these functions look like generally. So first, I want to talk about the quadratic function. If you notice, it looks like a U. Now, the quadratic function and the absolute value function behave very similar to each other. They both either open all the way up or down. They're going to get narrower or wider in the same fashion. They both have a specific vertex and absolute lowest point on the graph. So working with quadratic should be pretty similar to working with absolute value, with the exception of, instead of taking the absolute value, the obvious, you're going to square the x term in order to get the y value that accompanies a given x. The cubic function over here has two bends in it. It comes up from negative infinity, makes a turn, makes a second turn, and goes up towards positive infinity. That is the cubic function. And of course, we could shift that left, right, having it change direction, so it might come down from this side and turn, and go down infinity on the other side. The next one is our square root function, our last one. Square root function starts at 0 and heads off into positive infinity in both the x and the y direction. Eventually, we'll head over to the cube root, but for now, we'll just stick with the quadratic, the cubic, and the square root for our newbies. So let's move on and tinker around with some of these. Before we go too far though, take a minute and copy down all of the functions, get them all in one spot. Copy down the linear and its picture, the absolute value and its parent picture, the quadratic and its parent picture, the cubic, its parent picture, and the square root and its parent picture. You want to have a basic understanding of what these graphs look like in their parent form and the parent equations that go along with them. So copy down those pictures, copy down the names of each family. Press pause now. So what we want to do now is we want to build a table of values that's going to go along with each of our parent functions, the new ones. So you already know the f of x equals the absolute value of x, and you know that negative 4 goes with positive 4, and yada, yada, yada. So now what we're going to do is we're going to work with the quadratic. So first, let's build our table. So we're going to build a table, x and the y value that accompanies x for any given value of x. Let's substitute in some values. Now we want to think about this. Well, what values, Mr. Brecklin? Well, again, remember that this picture stems on both x and negative x, so we want to come up with some negative values of x and we want to come up with some positive values of x. But now remember, this thing's going to get big really quick, so we don't want to use too big of a value for x. So let's just do a handful. How about x of negative 3, negative 2, negative 1, 0, 1, 2, and 3, and let's evaluate those. Right? So what is the value of negative 3 when we apply it into the function? If I substitute negative 3 in for x, I square negative 3, I get positive 9. If I square negative 2, I get positive 4. Negative 1, I get positive 1. 0, I get 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And now I have a nice handy set of 7 values that I can place on my graph over here. So draw yourself a quick sketch of these points right now. I'll give you a second. Okay, you should have something that looks like my graph. Notice I was only able to plot the y values that go with x of 1 and negative 1 and the y values that go with x of 2 and negative 2 because my graph doesn't go up to positive 9. But what you should have is a smooth curve, a vertex of 0, 0, and I guess I should follow my own advice and make sure that my graph's neater, but it's actually kind of hard to write very, very accurately on this program. So I'm doing the best I can. I hope you could extend me a little bit of leeway there. Next we have our cubic function. So what do I want to do here is, again, make a table of values for x and the y values that go along with x. Again, taking into consideration that our y values are going to get pretty big pretty quick. And again, it comes up, makes a double turn, and goes right through here. So we know we need some negative x values. So I'm going to go with negative 2, negative 1, 0, 1, and 2. And I start evaluating for those given values. So when I take negative 2 and raise that to the third power, right, I'm going to get negative 8, because a negative number raised to an odd power will always be negative. Negative 1, therefore, to the third power is negative 1. 0 raised to the third power is 0. 1 times 1 times 1 is 1, and 2 times 2 times 2 is positive 8. Take a minute again, of course, and you guessed it, draw the sketch. So, again, do you have something that resembles the cubic parent function that was on the first slide? I hope so. Moving on. Now we have our square root function, and we know that that square root function started at 0 and went off to the right, climbed slowly. And why is that? Well, grab a calculator and try to take the square root of a negative number. As we've talked about that in class, the square root of a negative number is an imaginary number. Right? It's not in the real number system. Therefore, it's hard to take anything, the square root of anything that's less than 0. So I guess a good starting place for the parent function of square roots is to start at 0. And so we'll go 1, and then we have a problem here. I guess I only want to use values of x at this moment that are perfect squares. So after 1, 2 times 2 is 4, 3 times 3 is 9, and 4 times 4 is 16. So I'm looking for what kind of numbers are these. They all have something in common. 0, 1, 4, 9, 16. They are, what's that you say? Perfect squares. Okay, so the square root then, when I want to evaluate, say, f of 16 is equal to the square root of 16, so f of 16 is equal to 4. So this is 4, square root of 9 is 3, square root of 4 is 2, square root of 1 is 1, square root of 0 is 0. And now I can plot my values. Take a minute, draw your sketch, and hopefully it looks like the parent function of the square root function. Now again, I'm limited by the number of lines on my graph, and of course, yes, I can change the scale if I wanted to, but we're just looking to get some basic pictures here. So this is the ultimate moment now. We're going to apply your transformation knowledge, of which you already have, to say the cubic parent function. What's going to happen here? And so, in taking a look inside the function, we see that we have an x minus 2, which we know that that means that we are going to shift right 2 units. We also see that we have a plus 2 on the outside of the function, which means we're going to shift up 2 units. Our a value sitting way out here is 1, which means as far as the scale factor is concerned, we're not going to multiply y's by anything other than 1, which means the y value doesn't change, and we're not going to reflect. So let's go back from a few slides ago, and let's steal those values, just enough to get the job done, to draw our parent function. Go ahead, look at your notes, and transfer that parent function onto the current graph. Alright, you should have something that looks like the purple line that I have on my page. And now what we want to do is we want to evaluate the red function, right? The transformed cubic function. So we're going to take our x and our f of x, and I'd like to know what happens. So we've gone through this in class, and this is a pretty simple one. What's going to happen is, since we're shifting to the right, we're going to add 2 units to x, because we're shifting to the right, and then we're going to add 2 units to y. And what's going to happen when we do that? When we shift and we add 2 units to x, we're going to end up with 0. And when we add the 2 units to y, we're going to end up with -6. You add the 2 units to 1, right here. When you add the 2 units to -1, you're going to add up at 1. And when you add the y, 2 units, you're going to add up at 1 as well. Take 0, 0, becomes 2, 2. 1, 1 becomes 3, 3. And 2, 8 becomes 4, 10. And plot those on your graph and see what happens. Now, as you see, I can't graph 4, 10 on mine, but I guess the question is, does it look like the purple graph shifted up, shifted right? It looks to me as if this point right here went up 2 units and right 2 units, and this point right here went up 2 units and went right 2 units, and this origin piece went up 2 units and right 2 units, and our original 1, 1 went up 2 units and right 2 units. So it looks like the transformation happened just as we expected. And this is what we're going to be doing in class. It's just looking at the cubic, quadratic, various families of functions, applying transformations, redrawing the pictures. Piece of cake. Hopefully you have good thorough notes. Bring these to class, and we'll see you next time. Bye-bye.